Hi. I hope everyone is having a nice Friday. I was a little bit lazy with my cosplay today. I didn't even do much makeup and stuff, but today we have a super exciting topic. So I hope everyone is doing all right. So hi Riyadh, Kachel, uh maybe not Rob, Daliard, Juster. So hi everyone. I hope everyone is having a nice Friday. I will say today's topic is going to be a bit of a lot. Um and I hope you guys will like it. Thank you P boy, PB boy for following. It's going to be a little bit of a the topic by itself is just a lot of content, and I will be honest here and say it was very hard to condense this in a way that can be followed by just anyone. Hi morning. Hi. Um so I really hope you guys will enjoy it. Please ask any question that comes to your mind, because this is gonna be a little bit of a topic that builds on itself and will be also relevant for the next part that we're gonna be talking about. Uh, okay, we'll talk about this later, but it's gonna be relevant for the next part. So if you guys want to have the slides, they're available on my Coffee page. So there are part two right here, and yeah, and so you guys can just download them here. If you want to just get them for free, you can just put 0 and you just download them. In case you guys want to take any notes or have maybe any particular questions, and want to point out where you guys had your specific question. So yeah, so I hope everyone is ready. Just a brief reminder of what we're doing. We're looking at the Bouken Desho opening from the first season of The Melancholy of Haruhisuzumiya, and as you guys see, there's a bunch of equations and a bunch of scientific expressions in the back of the opening, and this leads me to what my plan is for this series. So last week we covered astrophysics. This week we're covering quantum mechanics, but just the general overview of what the series is about is first of all documenting the background equations that I found in Bouken Desho, which is something that had never been done before to my knowledge. So just that we know which are the equations that are there and what they belong to. And I would like to deliver a bit of a comprehensive explanation on what these equations are. And I also want to tie them together with certain themes and certain characters in Haruhi, and just maybe why would they have picked these equations to be in here. Cave Wizard, not a game. Not a game. We do gaming sometimes, but not today. Not today. But yeah, so today we're gonna be covering quantum mechanics. So I want to give you guys a brief overview of how we're gonna cover quantum mechanics. We're gonna be building the topic up little by little. So we're going to start off with the Planck constant, which is one of the symbols that shows up in the opening. And we're going to talk about what is quantization in the context of how the Planck constant was first derived and why quantization was needed for physics. Okay, so a brief question before we start. How long did I prepare for today? I will be honest, this week was really tough to do everything. So I did end up spending quite a few hours in this because I really wanted to give a comprehensive overview quantum mechanics was personally one of the most challenging subjects for me in university, but I find it to be, I guess, my favorite, or the one that I appreciate the most. So I definitely spent a decent few, I don't know, maybe 10, 12 hours or so just trying to gather everything that I want to say and try to put it in a comprehensive way for you guys. So we're going to be covering a decent bit of content, but I hope to make it very understandable for you guys. So first thing is Planck constant. What is this? Why was quantization needed? What even is quantization? And we're gonna follow that with talking about basically one of the pillars of quantum mechanics, and one of the most cited equations in like a bunch of media, and you see, like, you hear about it everywhere. It's the Schrödinger equation. So we're going to talk about that in the context of what does a quantum representation of a system look like, and we're going to be looking at a particular example, which is one of the first examples that you ever see at university. And lastly, we're going to build that slowly, relating it to certain things in haruhi, but nothing too explicit. But by the end, we're going to talk about mainly what I think is the biggest connection between haruhi and quantum mechanics, and I feel like the deepest bond between the two, and why they chose these particular equations to be in the opening. And for that, we're going to be talking about different interpretations of quantum mechanics and how they tie into certain plot points, in particular in season 2 of haruhi, and also in the disappearance of haruhisuzumiya. So we're going to start off with Planck's constant. So there are two equations in here. It's really hard to see from the image, but you can just capture kind of what they say, and by the end we will basically bring them out and write them down ourselves. So we're going to be building slowly up the reason for quantum mechanics, and this is going to start by talking about heat transfer. So we're going to be talking about, mainly we're going to talk about heat transfer, and now just in general, there are three main methods in which heat is transferred. So first, you can transfer heat through fluids. So when you have a fluid which is hot, it heats up basically itself. There is some molecules that are hot, and then they go up, and then the other ones get heated. It basically heats itself up, and can heat other things up as well. But then we have the one that is direct contact, which is, when you touch something hot, it's transferring heat to your hand, so your hand gets hot. And then we're also going to be talking, and this is our main topic, it's going to be heat through radiation, through electromagnetic waves. Hi, K-Wizard, thank you for following. So, we're going to just briefly go over what are electromagnetic waves. This is something that we'll explore a little bit more in depth next week, but I just want to give a little bit of an idea of what we're talking about. So electromagnetic waves are waves that propagate at the speed of light. They're characterized by, first of all, their amplitude, and that is how strong they are. But mainly, we're going to be talking about them in terms of frequency and wavelength. So a high frequency wave are waves that basically oscillate really, really fast. By oscillating really fast, the wavelength, which is basically the period of repetition of the waveform, is shorter. Whereas in low frequency waves, you have basically a slower wave, which has a longer wavelength. So a longer period, it takes longer for the waveform to repeat itself. So we're going to be looking at waves more so right now in terms of their wavelength or their frequency, which I may use a little bit interchangeably, and that is just out of habit. But if you guys need any clarification, just let me know. So a question, is this how ocean waves work too? So ocean waves are characterized by a different set. So basically, these are the waves that you see, for example. These are waves that are coming from the sun that burn you, another example, that heat up Earth, etc. So these are waves that propagate through media, through electromagnetism. We will be a little bit more in depth next week, but this is not a physical wave in the sense of, an ocean wave made out of a bunch of particles. These are photons, and we're gonna be talking about it. So these are basically photons. These are basically light particles that propagate at the speed of light. My mind is heating away. I'm so sorry. So we're building up a little bit slowly, but I just want to clarify this in case there's any confusion. Okay. So frequency and wavelength are thus basically inverse proportional to one another, meaning that one is c, so this is the speed of light, divided by wavelength, and so on. So short wavelength, small, means high frequency. So a lot of frequency, small wavelength. A little bit of frequency means long wavelength. So inverse proportional to each other. And then the other main thing that we're going to discuss today is what is the electromagnetic spectrum, which is the spectrum of all the different frequencies or wavelengths. Like I said, I may use this interchangeably, so let me know if you need a clarification. But it's the whole spectrum of wavelengths that we can find. So this goes from really long wavelengths, like for example, the ones used for broadcast, radio, the ones used for microwaves. Then we get into a little bit higher, then it would be, thank you for following Green Taurus. Then it would be infrared. Then we get into the visible light spectrum, which these are all the range of wavelengths that we can actually see with our eyes, where we have basically integrated detectors in our head to be able to perceive these. Then we move on to ultraviolet, X-rays, and gamma rays. And the reason why these are typically, you will hear like gamma rays are dangerous, X-rays are dangerous, etc., like UV rays can burn your skin and so on. This is because these are really much higher energy than the waves that are not harmful for us, like visible light or infrared. So the higher frequency we go, the more energy that we have in the waves that are reaching us. But we will discuss this a little bit more in depth next week, but I would say these are the pillars that we need to build our understanding of why quantum mechanics was needed in the first place. So getting back to heat transfer, now that we've talked about heat transfer through radiation and what radiation means, so the transfer of basically the transfer of energy through electromagnetic waves, we can talk about what the ideas were regarding heat transfer. This was until the late 1700s. They used to think that we had two types of particles. Cold particles, like for example, let's say snow is made out of cold particles. This is all the knowledge back then. This is not reality, just to clarify. So back then they used to think, okay, snow is made out of cold particles. So when I touch snow, it is transferring coldness to my hands. And also when I'm touching something warm, like for example, a cup of tea, this is transferring heat to my hands. So they had these two types of particles that they considered existed. However, this is not the case. All objects can radiate. All objects radiate, in fact. All objects radiate, and this was an observation by physicist Pierre Prévost. Ignore my really bad French pronunciation. And he basically observed, number one, that all objects exchange heat with their environment, so that heat transfer is not restricted to only a specific set of objects, not only cold and hot objects, but all objects. All objects are exchanging radiative heat, in particular, which is the one we're discussing today, with their environment. Okay, let's see. The next thing is that he also observed that objects with different properties exhibited different radiative behaviors. So, for example, this is what we hear a lot during summer. If we wear black, we will typically get hotter because black absorbs more radiation. Whereas if we wear white, it will actually reflect a lot of the radiation and we are not going to get as hot. So this is something else that he observed. Let's see. And the next thing that he observed is the fact that heat transfer reaches an equilibrium. And this we also see, for example, when you heat up your room, let's say, you turn on your heater and the room will start heating up, and then eventually it will reach an equilibrium where everything is more or less the same temperature. Like things just become the same temperature with each other unless something changes. Unless you bring an ice cube and this, if you feel around the ice cube, is going to be colder than if you're away from the ice cube or things like that. So everything tries to reach a temperature equilibrium. So here's an example. If I have a block A, which is higher temperature, and a block B, which is lower temperature, if I put them together, heat is going to flow until they both reach the same temperature. There is a question. I feel like old knowledge makes the world more magical. Yeah, sometimes knowing less makes things sound simpler and maybe more exciting, or maybe it's just that you know less, so there are more questions, but at the same time, the answers are just very imaginative. If I put my cell phone inside a microwave, it's radiation that destroys it rather than the heat. So I believe it's both, because so basically the purpose of microwaves is to make water molecules vibrate, in that they start moving, and they become hot. So I don't know what actually kills the mechanism, like what is the first thing that dies in a cell phone, but basically when particles are radiated at a particular wavelength, they will start to vibrate in such a way that they get hot. And that is particularly how you transfer heat through electromagnetic radiation. Okay, so following these observations by Mr. Prévost, or I don't know, excuse my French, he thought about matter, he thought about radiation. These physicists started considering an ideal object called a black body, which is an object that absorbs all wavelengths of radiation. So if I have a completely black object, basically, that just absorbs all radiation, what does it give out? If everything is absorbed, I need to, the obvious question is, what do I measure if I measure radiation from such an object? Assuming there is no water in cell phones, then what particle moves? Well, the issue is there's water in the air. There's water all around. So I also don't know, the inner mechanisms. I don't know what the materials are inside. So, but even then, there's moisture in the air. There's moisture all around. And yeah, isn't that due to the electromagnetic field in the microwave? Yeah, I assume you're kind of, I think you're just saying, in other words, what I said, which is the microwave basically radiates at a particular wavelength. And this wavelength is chosen in particular so that it excites water molecules to vibrate and to heat up. So the electromagnetic field, in the sense you're describing, it's a little complicated. Like the way the way it's phrased is basically, it's simpler to say electromagnetic waves, because electromagnetic waves are partially an they are partially an electric field and they're partially a magnetic field, as the name suggests. So yes, it's the electromagnetic wave itself and not the field in a sense, but it's the waves itself that are being sent. I hope that makes sense. I hope I phrased it in a nicer, understandable way. The radiation causing too much power being made in the cables, melting and overloading the battery. I'm not exactly sure what kills your phone, but I know that inside a microwave, you're basically just radiating electromagnetic waves at a particular frequency or wavelength, which is chosen in particular to affect water molecules. So I don't know what is inside my phone, but in general, that is what happens. It also could be that, because this frequency that is chosen is specifically chosen for water molecules, but these can also be absorbed by other molecules. So I am not saying that the heat inside a microwave is not absorbed by other molecules. Could be some sort of silicone inside your phone that also gets heated up. Could be some of the other circuit components that also get heated up. I just mean that the particular wavelength chosen is chosen for water. So I hope that more or less answers the question. But yeah, getting back to what we're talking about, black bodies, they are an object that absorbs every single wavelength of electromagnetic radiation. Thank you, Eggcast, for following. And we're trying to see what comes out. So, a way in which you can simulate such a thing in an experimental setting is by having a sphere with a teeny tiny hole in the sphere. And just a hollow surface, like basically it's hollow inside. And inside of your sphere, you will have a very absorbent material. So some sort of really black material. And what happens is that you basically shine radiation, so whatever electromagnetic spectrum you want to send in. And what will happen is that it will bounce around, and it's very unlikely that it will actually escape. So it's really close to a black body where it absorbs almost every where it absorbs almost all light. So it's a good approximation, at least for the practical sense. And then this sphere in particular is at a temperature T. So this is at a constant temperature. Radiation is only dependent on the temperature. That is the particular meaning that there is no heat transfer with the environment at this point. It's found at an equilibrium. So following this, they had the observation, which is this black curve right here, where they tried to see the spectrum of the light coming out of the little hole. So what actually comes out of this little hole with respect to the wavelengths. So to get a spectrum of what wavelengths of light are coming out of my black body radiator. And the observation is this black curve we see right here. Following this, they had some attempts in trying to describe this through the means that were available at the time. This was in particular through something called the equipartition theorem, which is basically the relation of the system to its average energies. And yeah, a lot more complicated and in-depth that we would like to discuss here, but mainly the point is the curve that was predicted through these classical means is this red curve that we see over here. And this red curve caused something that at the time was called the ultraviolet catastrophe. And that meant that it seems like the red curve follows the observations very closely up to a certain point at the really high frequencies. So in the ultraviolet X-rays and beyond, where we see that we just see a complete increase into infinity, where we have an uncontrolled amount of radiation that doesn't really match what we observe. This would mean that basically the sun would be radiating at frequencies that would basically cook us alive because it's so much energy. So not particularly would we observe in our everyday life either, and not what they observed in this practical or experimental examples that they looked at. So after this whole discussion, there was a famous physicist called Max Planck, and he proposed looking at the problem at basically the energy output of the emitter of the black body, instead of as a smooth curve of energies flowing, as steps. And so the classical model would be basically just energies flowing smoothly, like little by little, as if energy from my electromagnetic waves were being deposited smoothly. Instead, Planck described it as packets. So there's that more in terms of an actual particle, of like an actual photon that is like hitting one photon, two photons, this much energy, this much more energy. So just in steps of energy and not as a smooth flow of energy. Thanks for following Fear Hard. So instead of describing it as a smooth deposit of energy, he described it as stepwise. And this is quantization. So when you hear quantum mechanics, this is basically what it means. It means small packets of things. That's really what it means. It's a really cool word, but this is basically what quantum means. Things that function through quantum mechanics, and quantum mechanics describes objects that behave in this way, like light, for example. So this is the law that he came up with. We're not going to worry too much about the math, but I just want to point out here is where we first find our beautiful H, our beautiful Planck constant. So Planck constant, he determined it to be this factor of 6.62607,015 times 10 to the minus 34 joule seconds. And yeah, just for completion, c is the speed of light, and kb is the Boltzmann constant. And this b of my frequency and t is the spectrum of my black body radiator, at a particular temperature T. So I put my black body radiator at a temperature and I see what frequencies of lights come out of it. And this is my spectrum, B of frequency and T. If you guys have any questions until now, just feel free to ask. We'll also have a little bit of a moment for questions. But if anything comes up in a particular slide, feel free to ask. And you know, we saw the beautiful formula, really nice, but how does it look like in an actual graph? I feel like that is a lot more representative. So we have our power, intensity, or we also called it radiation density. The units are a little bit arbitrary at this point because we're not really talking about anything too specific. We want to talk about the shape. And the curve itself has this particular shape where we have a specific peak here and then it falls. So very similar or almost the same as what was observed in many practical curves are for a different temperature. So this is a high temperature, a couple of middle temperatures, and then some smaller or lower temperatures, sorry. So we observe that these are very close to the experiments that were conducted trying to describe what the spectrum of radiation is from a black body. How did Planck derive his constant? So I actually read up a little bit about this. I am sure I linked one of these papers. If you guys download the slides, you can have a look at it. But he said he just made this assumption of the stepwise energy increases, and then he just checked what came out. For him, it was kind of an arbitrary choice. He was a theoretician, and that's kind of what theoreticians do to some extent. They will make an arbitrary choice, and then he went back and he tried to justify it in different ways. Thank you for following Mew Mary. But interestingly enough, this exact number for the constant can be derived a few different ways. I personally have actually had to derive the Planck constant for one of my labs in my undergrad. And you actually do that by looking at something very similar to this fake ideal black body. So the closest thing that you can get experimentally to a black body. And, it's a little bit of math in between, but you can both derive the Planck constant through a few theoretical means, just looking at the actual theory of black bodies, harmonic oscillators, blah, 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 a bunch of math. You can derive it that way, like Planck did, and how other people have done different ways. And you can also confirm it through experimental means as well. Yeah. Okay, sorry. Arbitrary choice, so he kind of made it up and see if it sticks. Yes, and that is actually how a lot of things in theoretical physics work. People will make some arbitrary choice sometimes. I'm not saying all of the time. Sometimes there are very justified choices. But sometimes they will make an arbitrary choice and then see if this new approach actually can describe reality better than some other approach. What else was there? And a really nice 3D graph having temperature on the z-axis. Yeah, that would be interesting. That would be a pretty crazy graph, I think. Yeah. Okay, and then now we're finally arriving at the equations that were shown in the Haruhi opening. So the first equation that we saw in the Haruhi opening is h bar, which is, as the slide says, the reduced Planck constant. And this is just the Planck constant divided by 2 pi. Not, maybe it also sounds very arbitrary at the moment, but this is something that is done more so for computational reasons to make things look nice and fancy. Thank you, Adcast, for subscribing. So this is just something done for practical reasons to make writing a little bit nicer, because it looks a little bit nicer with the little bar. So this is called the reduced Planck's constant, or h bar. Most often people will say h bar. And then the second thing that is shown in the opening is the value for h bar, which, as we saw from just the Planck constant, we take the Planck constant, we divide by 2 pi, and we get 1.0545, so on, times 10 to the minus 34 joule seconds. And that is the 2 equations that you see in the opening. For polar coordinate shenanigans, I assume. What did you mean, frolic? I'm not sure polar coordinates where. But yeah, so as the ones that were here last week, we also saw that we had this constant called the Hubble constant. But now we have another h. We have I believe that another H was in particular chosen because Haruhi's name starts with H. So I think that they were definitely gravitating towards choosing constants that had, choosing equations that had a lot of H's in them. And in particular, you just see this a lot in quantum mechanics. We have the small h, and we'll see a new h next time. An h with a hat? No, this time is an h with a bar. The h with the hat is coming in the next equation, so don't worry. Don't worry, h hat is coming. I was thinking for the integrals with h bar, but I guess not. So yeah, h bar is really just a definition to make the constant look nicer. Scientists love naming things after themselves. I believe this was just named the Planck constant because he was the one that derived it. I'm not sure if he actually named it that way. Maybe. A lot of these things are done after the fact. Like, they just become like, oh yeah, that constant that was introduced by this guy. Ah yeah, let's just call it this guy's constant. So I guess you just see that a lot. Does H always mean something similar? So H as in Planck's constant always means Planck's constant, but you can obviously use H in different contexts. Sometimes people use it for denoting height. Sometimes people will use it for denoting, well, last time we saw a big H, which means Hubble constant, for example. But if you see H in any equation that looks very complicated and has weird notation, it typically is just quantum mechanics. But yeah, in the context of quantum mechanics, I cannot really think of a different H that you ever use. And in particular with a bar, it just becomes unmistakably H bar, unmistakably reduced Planck's constant. But yeah, so short pause. Let me know if you guys have any questions. I will just drink a little bit of tea. Have a really big bottle of iced tea. So let me know if you guys have any questions or anything that was unclear. Sorry if I don't have any better explanations as to why your phone explodes in the microwave. I would assume just the molecules in there are still heating up, are still absorbing the electromagnetic waves that are set by your microwave. But I don't know what materials exactly, like I don't know why in particular it kills it. So sorry about that. This is lime, or no, lemon. Yeah. It's like how Shannon named one of the main concepts of information theory entropy just to troll physicists. Yeah, we also have the Shannon entropy equation. Actually, this was also something that came up in the opening. I will cover this probably in the fourth. I think it's gonna be 4 parts, this entire series. But yeah, Shannon entropy also in the opening. to my surprise, and to well, I only really looked at Shannon entropy in the context of thermodynamics, obviously, so not really in terms of information theory and so on. So that one is definitely going to take me a little bit of time to just go over the literature, because it's not something that I ever covered outside the context of physics. It's interesting how colors of fabric and radiation is used with farming. Over here, they always cover animal ferment with black tarps to make it ferment. Yeah, that is also really cool. I'm not in the field of physics, but in anatomy, anatomists love to name things after themselves, I'd assume. But this is interesting. Yeah, I don't know. I guess it typically makes it a little bit simpler because you just say, okay, it's the thing that this guy introduced. So that just makes, okay, obviously, yeah, that one thing that this guy is known for. I feel like the hardest ones are the ones that have a lot of things named after themselves, and it's like, oh crap, which of the many things? Like, interestingly, calculus is not called like Newton calculation methods or something like that. I bet if someone was named Gregor, Gregor but Polish, Gregor Bizershurt, they wouldn't name. Yeah, they would definitely not name discoveries after him. So, or they will, or people will mispronounce his name like Euler. Everyone calls him like Euler or other weird or Wheeler or other weird names. Which is the best Haruhi equation? Maybe the next one that we're gonna talk about, I think. It's a lot cooler to name things after Pokemon. Very true. My channel is named Pikachurin after the protein. Yeah, there's Newtonian, there's Lagrangian calc. That is true. That is true. But yeah, it typically just, in a way, is helpful to name things after people, because then you're like, okay, this is the thing that guy is known for. So we're gonna talk about an equation named after another person. That's a great segue into our next topic. So we're gonna talk about the Schrödinger equation, which was an equation introduced by Edwin Schrödinger. And okay, my camera is kind of glitching, so I'm sorry about that. But I hope you guys can still hear me just fine. But that is going to be this equation right here that we see. So we're going to move on from talking about light to talking about matter. So we discussed radiation of electromagnetic waves, so of photons, and we describe them as basically discrete energy packets that deposit energy in little steps. But this concept was also extended to matter particles. So in particular, we have basically two questions. One of them, which is, could matter itself have unexpected properties? Like, could it have properties that can't be described through classical means, such as describing black bodies didn't really work with classical means? This is something that will, for the most part, be covered next week, but we're just going to discuss it a little bit here. And also the second question is, could matter also behave like waves, just like photons do, like we saw before? So about the unexpected properties and so on, that we're going to discuss a little bit more depth next time when we talk about particles. So we're going to talk, first of all, about basically the main tool that you have in quantum mechanics. And this is, or at least, I'll just stop myself. So the main tool that you basically have in quantum mechanics. So this is, yeah, my camera is going kind of crazy, so I'm sorry about that. Maybe I'll turn it off if it's really bad. I'll restart it. I'll restart it while I talk. So, the wave equation, the wave function is the main tool that we have for describing quantum systems. So systems that functioned through that function quantum mechanically. Right now, I'm not giving a lot of definitions for these things, so I'm sorry, but we can go just slowly. And they are represented usually with something called bracket notation, which are these. So this is a ket, and it's just a line and a little like triangle bracket, and a bra would be this, but the other way, so where we have the pointy bracket on the other side. this is just a way of denoting it. We're not really going to talk about linear algebra. We're not going to talk about all of the complicated stuff because I want to keep things simple. But just if you see this notation, this is just a type of notation used particularly in complex vector spaces in reference to quantum mechanics. Bracket mention, yes. Really cool notation. Also why I included it. So, important properties about the wave function. And this is the really important part. The wave function, when I do, I will say this in complex terms first, and then I will describe what that means. So when I multiply my wave function by its complex conjugate, in other words, when I multiply it, when I multiply by itself, taking the absolute value. A little bit, a little bit charged because we're talking about complex vector spaces, but basically when you multiply it by itself, I'm sorry, mathematicians, do not kill me. It gives me what is known as the probability density. And here we have a really beautiful example, which is the wave function of an electron and its distance from the nucleus. So here we have the behavior of my probability density, and here we have the distance from the nucleus. So this is giving me the probability of my electron being a certain distance away from my nucleus. So this is a really beautiful example because this is one of the particular challenges of things that was a little bit difficult to explain through classical means, and quantum mechanics gives us a really beautiful and elegant way of explaining this particular phenomenon. Basically, people used to think like, why don't electrons collapse into the atom if the atom, into the nucleus, if the nucleus of the atom is positively charged, and so on. And this is something explained very beautifully through quantum mechanics. And then, so this gives me the probability of my particle, in this case an electron, being somewhere a certain distance from my nucleus at a given time, in this case. PDF distributions mentioned. I just failed the test about deriving those. So sorry about that. But yeah, if there are any questions up until now, please ask. I want to make this part very clear because this is going to be our pillar into discussing the equation itself. So, so wave functions describe quantum systems, and by multiplying the wave function by itself with a little bit of quotation marks in that, it gives me the probability density, basically where my particle is at a given time in this example. So please let me know if you guys have any questions. No question is too dumb. This part is kind of the complicated part where we talk about things that we maybe have a little bit of a hard time imagining in our heads. So yeah, if you guys have questions, please just ask. So now we move on to, now we see the H hat. So Dalliard, I think, mentioned the hat. This is what is known as the hat. This little triangle here. This is our H hat. Most of it is hocus pocus to me, but it's still really interesting. Yes, this is very theoretical, and discussing this without discussing the math is a little bit complex, but I will give, by the end of this, a take-home message, which is, even as someone who doesn't know the theoretical background, if someone shows me the Schrödinger equation, what does that mean to me? H with a cute hat. Yes, very beautiful hat. Is the support for that PDF distribution all real numbers or just all positive real numbers? By the support, do you mean, so basically the wave function is typically some sort of how can I explain this? We're typically gonna have some form of e to the x squared divided by some value. So it's gonna look very similar to just a normal distribution, kind of. So there is, you have a complex exponent, but the actual values of my x are all real numbers, if that is what you meant. This is such a nice refresher for physical chemistry. I hope so. Maybe it's a little bit of a more comprehensible overview, maybe in the terms of what a chemist would think about. Okay, yeah, so for all like you, because you're a math guy, this is basically a normal, like the wave equation in a lot of these cases basically kind of looks like a normal distribution. So my probability density is basically a normal distribution. So I hope that answers the question. Okay, so the Schrödinger equation. What does the Schrödinger equation tell me? So it tells me mechanics at the atomic scale, at the quantum scale, the very, very small scale that we cannot talk about through classical means. And it tells us, this particular equation tells us how my psi, so my wave function, changes with time. So this is why we have a time derivative here. I'm not going to go into what calculus is and what derivatives are, but derivatives basically describe change with respect to something. In this particular case, change with time. We have our famous h bar, which basically brings us to this really tiny scale, and then I, which is the complex factor square root of -1, which again just helps to basically our wave function has some real and some complex parts to it, and this I just helps us keep everything in check, so to say. So these are just numbers that help the rest of the equation remain cohesive. And this is equal to our h hat and my wave equation. This is what is typically known as a differential equation, where I have an equation and a derivative of an equation, and then I need to find what the possible solutions are. This one is a particularly interesting case. And the other interesting thing about the Schrödinger equation is that it basically is a quantum equivalent of Newton's second law, but for quantum systems. So Newton's second law tells us it's the famous F equals ma, but in words it tells us how is my system changing with time. If I push this card and I give it a shove and it gets this acceleration, how does it move with time? That's basically what Newton's second law tells us, and this is basically Newton's second law, but for quantum scale. So we're going to talk about this interesting h hat now. So this is known as the Hamiltonian, also named after someone, and this is an operator. Right now I'm just using this term because it's a very, in a way, specific term, but by operator, I mean basically a series of operations that act on my wave function, and they correspond to the total energy in my system. So they correspond to both the kinetic and the potential energy of my system. When I apply this operator into my wave function, out of it, I get the energies of my system. And we're going to talk about this a little bit more in a second. So if that is unclear, I think I will make it clear by the end of this part. And this basically means that the solution to applying my operator h onto the wave equation gives me what are known as the eigenvalues. They're just the solutions that give me all the possible energies of my system. Again, I will exemplify this hopefully very nicely with one of the simplest examples we can think of. So for this part, my main message, and if you are a little bit lost, I am so sorry. Please ask all the questions that you need to ask. But my main message that I want to send with this is the Schrödinger equation gives us a way to calculate how my wave function changes over time. So that's already something. We're talking about wave function, so you learned wave function is an object that describes quantum systems, and this equation tells us how these quantum systems change over time, allowing us to predict probabilities for different outcomes, allowing us to predict probabilities for different outcomes as it evolves through time, and the different possible energies that it can take. That is really the basic knowledge of what this equation is telling us. Eigenvalues. That's the only thing I remember from my intro to linear algebra. I will say, please, if anyone has a question, ask in the chat. No question is too dumb. I will make my best attempt to answer all questions. Eigenvalues, and then what I wanted to say is I was actually talking a couple days ago about this, the fact that after you go to linear algebra, I personally don't remember maybe 2/3 at least of what happened in my first linear algebra course. However, I was just thinking, if you go to linear algebra, I feel like the main things you need to learn are just how to compute eigenvalues, and that's kind of it. That is kind of it. I will say, like, what are vectors? How do I compute eigenvalues? That's kind of it. What are eigenvectors? Everything is solved. If you forget how to diagonalize a matrix, you just look it up, whatever. Don't worry, they didn't even teach us algebra in high school. Yeah, I think I pretty much just learned linear algebra in college for the most part. I mean, I talked about vectors in high school, but I never talked about, actual, computing eigenvalues, matrices, etc., etc. So I actually learned that in college as well. The thing is, I don't think I know enough now to even formulate a dumb question. Okay, so maybe I will try to rephrase this in even terms that maybe are even simpler than this, because this is a little bit of a charged statement, adding wave equation and so on. But the Schrödinger equation tells us how things at the atomic scale, for example, an electron orbiting around a nucleus, how this electron behaves over time, and what the probabilities are that it has a certain energy or some other energy. That is kind of the gist of it, and I hope I will illustrate this nicely with the example that we're gonna follow in a second. I think I only took that because we need eigenvectors for regression analysis. Okay. Yeah, you need a lot of linear algebra and physics, I will say. But yeah, so I mainly think that they chose the Schrödinger equation because it has another H, and because at the same time, our first H was an H that basically dug deep and gave us a view into the quantum realm, basically brought us to a really small scale. And now we have a new H that gives us a lot of information about all the possibilities. And I think this really relates to just haruhi kind of being the object or the being that brings us into really weird things. She brings us just how small h brings us into a scale of things that we can't really think about. Haruhi really brings Kion into a world of things that he can't really grasp, things that he can't really explain too well. So I think, there's a little bit of a deep connection between these two things, because the two H's in this theory really give us so much information. They give us, first of all, the scale of our system, and then the energies that we have in our system. So it gives us a lot of information. It lets us see what the possibilities are at the quantum scale. Um, only only math I was good at was discrete mathematics. I actually never had discrete mathematics. So that's already really good. But yeah, so if you guys have any other questions, feel free to ask. But following this explanation on the Schrödinger equation, we're going to be talking about a specific example, which I hope will be the one that really brings it together for anyone that's still feeling like they don't really understand what we're talking about. So this is going to be the time-independent Schrödinger equation. Very different from what we saw, obviously. So time independence, whenever you hear time independence, it means it's going to be a lot easier. That's basically what it means. When we don't care about time, things get a lot easier. So I just want to preface this by saying I think it's going to get a lot easier to understand. So the time-independent Schrödinger equation gives us the stationary energy states of the system. Okay? In other words, it gives us the possible energies of my wave function, this guy right here, when it's not evolving in time. We don't care what happens to it afterward. We don't care what happened to it before. We just care about what are the possibilities at this very moment where I have this description of my system. What could be the possible energies that I can measure in my system at this very moment? So I hope that is clear to this point. And this is what the equation looks like. And now we're going to move on to an example. So we basically are going to be talking about the example of an electron in a potential energy box. We're going to explain it little by little. But yeah, so we're talking about an electron, for example, which has a particle, whatever particle, maybe just a general particle is better to think about. So we're going to talk about a particle, and particles will have a kinetic energy part of their Hamiltonian first, which is the motional energy. And here we have this Laplace operator, which is basically calculus, blah, blah, blah. But we just care about the fact that it's change in space. So change in space here denotes change in momentum. And change in momentum, or the relation of, this is basically change in space, and this is related to our momentum. And our momentum gives us our kinetic energy, and this is why this is the kinetic energy operator. We don't really care about the specifics of where it comes from, but just know this is the kinetic energy operator. And then we have our potential energy operator, which in this example is going to be, I hope, very simple. It's just going to be a potential that we call V. And V is going to be 0 from our point of reference 0 to a certain distance L. And everywhere else is going to be infinite. So everywhere else our particle cannot be. Our particle can only be in this area where there is a potential going from 0 to L. Because everywhere else the potential is infinite, meaning that it's basically just kicking out my particle. So by rearranging the two definitions for the potential and the kinetic energy that were in our H, and just rearranging it all in the left side, we get to the equation that is actually shown in the opening. So this is the differential equation for solving the time-independent Schrödinger equation. And this is, right now, I really don't want to focus too much on the actual equation itself, but I want to talk about the solutions of the time-independent Schrödinger equation in our particular example. So when we have our particle in this basically potential box, where it can only be in a specific length from 0 to L, our energy is going to be quantized. So when we solve our equation, we're going to get an expression for energy, which is going to be have a bunch of different solutions. And these are all the possible solutions that we can get for the energy of my particle. So there are n different solutions. And when we go, for example, if my first solution is the one that I picked, it's going to be at this level. If it's N2, then we're going to have a higher level, and so on. But the important thing and the take-home message from this is that here you can very much see how the energies become split and quantized. And we don't have anything between these two energies. The energies can only be in these specific packets of energy. It's my main thing that I want to say with this particular example. I think that is kind of what I wanted to say. Unless there are any questions, because I think I went over this a little bit quicker than I was hoping. So L can be any length, really. This is just an example to illustrate what it actually means when I solve for the energies of my system. So when I solve for, so when I apply my H into my wave function and the energies that come out after solving the differential equations, so that they are quantized in different levels. Is this what they study with particle accelerators? Actually, not really, with some caveats, but we're actually going to talk a lot more about particles next week. So this is more so for particles at really low energies, where you can actually study single particles or single ions, for example. Whereas in particle accelerators, the aim is always to have really high energies. Basically, the aim in particle accelerators is to have energies so high that things start to not make sense anymore and other things come out. So, we're going to discuss that a little bit more in depth next week. I hope that's a little bit of a good thing to catch you guys' interest in that. L is not supposed to be arbitrarily small. It can be any length, because this is really just an example. Hope I answered that. And then, what is my favorite ice cream flavor? Maybe vanilla, cookies and cream, something like that. I'm sorry if this is a lot of stuff. But I promise we're going to get to the exciting part where you maybe will have more questions, and which is the part that really, really ties in deeply with haruhi. So, I hope this is more or less clear. It is a little bit difficult to explain this without the math behind it, but the take-home message is when we solve things using our Schrödinger equation, we get quantized levels of energy, just like we saw with black body radiation and Planck's theory on how energy from radiation is emitted. So please, at any moment, stop me and ask questions. But now we're going to talk about the very haruhi part. So now that we've gone over slowly all the theory behind quantum mechanics, I hope it makes a little bit of sense. We're going to talk about how quantum mechanics is interpreted. And we're going to talk about the deep tie-ins with certain plot points in haruhi particularly. It's a really, really dumb question, but how do you apply the formulas? Do you guys use a computer program or something? So, actually, for most cases, these are formulas that are very complicated, and they're typically done by theoreticians. A lot of these examples that you can compute yourself, you tend to do on by hand for the first few couple of months, for example, in a quantum mechanics course. But eventually there are methods in which you can actually simplify really complex systems. So yes, you can compute a lot of these by hand, but most of the time they're doing it in a computer. But I don't know of particular programs that people use to solve these, other than I had a course on, for example, using Julia, and I also, which is a programming language by, I forgot, I think it's Harvard or something like that. And I also had a course where you could basically just kind of do it whatever in Python or whatever, but I don't know if there are specific programs that theoreticians use to compute really complex systems. I personally don't really deal with these kinds of problems normally. I hope that answers the question. That was a little bit rambly. I'm so sorry. But yeah, back to, we have discussed a little bit about what's going on. Thank you, Lucas, for following. So we've talked a little bit about what's going on, and now we're going to talk about how we interpret this complex theory. Like, what does it mean to me in my life? Could this have an actual philosophical meaning? Could this have like a deeper meaning than we're just describing some system that we can see that is really tiny? And for that, we're going to first talk about the endless. It is a series of 8 episodes in Haruhi season 2, where basically the same day is repeated over and over and over again with slightly different things that happen. So this is number one plot point in Haruhi, where, this is very weird. Number one distinction between the novel and the anime is the fact that Kion, in the novel, he does not remember experiencing the same day over and over again. Whereas in the anime, he does have a recollection of experiencing the same day over and over again. So I would say that we should keep the novel interpretation a little bit more in mind, but we're going to get to it when we discuss it a little bit further. And the second thing that I want to discuss is the movie, The Disappearance of Haruhisuzumiya. So in this movie, Kion is basically in a world where the SOS Brigade is no more. Haruhi is nowhere. Everything that he knew from, the first 2 seasons of Haruhi is not there. Haruhi, she is in another school. Everything is just completely different. It's a whole other world, different to what he himself experiences. So the common theme between these two plot points, yes, many worlds interpretation. Yeah, the common theme between these two plot points is the fact that we have a slight deviation between things. The same people are there, but some things happen different. Some people have slightly different personalities, some objects are different, etc., etc. And this ties in with, as Kachel suggested, the many worlds interpretation of quantum mechanics. So now going back to our quantum terminology that we used, it tells us that the wave function is real. The wave function, the mathematical expression that we use to denote our quantum system, is a real object. This is what many worlds interpretation suggests. And because it is a real object, when I, as an observer, measure my wave function, so I measure the energy of my electron in the box, I become correlated with the measurement that I performed. Meaning, and here they put it very nicely, meaning that I, my present self, becomes correlated with this measurement, and the universe branches off in all the possible outcomes that I could have measured when I measured, for example, the energy. And this is also an interesting interpretation because there is no what we call the collapse of the wave function. By collapse, it means that when I measure it, it is this value and this value alone. And this is my reality at the moment. This is my measurement that I observed. And this is the only reality that to me exists. So they argue for the complete opposite. The wave function does not collapse. We have just as many worlds or just as many universes in where a different measurement was extracted. So this is what the many worlds interpretation of quantum mechanics tells us, and this is very similar to what we discussed in the Endless Eight and in the Disappearance of Haruhi, where we just have sort of a different universe where, you know, things are similar, but things are also slightly different, as if I made a different measurement in each universe that took me to a different outcome. However, with the caveat of, like I mentioned in the Endless Eight, in the anime, Kion does have a memory of what happened in these other universes. In the manga, this is not the case, and this is closer to what we're talking about. If you interpret it in this way, you don't have any knowledge of what's going on in any of the other supposed universes. So is there possibly a universe out there in which I understand what you're talking about? I am so sorry. I'm trying my best. We can go over this even slower next time. I'm so sorry. I really am trying to make it as understandable as possible. So we discussed this many worlds interpretation and how it ties in so deeply with these two plot points in Haruhi, but I want to argue against it. So I find the many worlds interpretation, very sci-fi, I guess is maybe the right word. So I just wanted to present, this is not my particular view of quantum mechanics, but I just wanted to present maybe what is the most accepted view of quantum mechanics, which is called the Copenhagen interpretation. So in the Copenhagen interpretation, the wave function is simply a mathematical tool to describe quantum systems. So it's just a mathematical tool. It's not a real wave function. It's just a tool. And following this argument, after I perform a measurement, my wave function collapses to a specific state. So when I measure this energy, this is the energy. There is no arguing about it. There is no other universe where the energy is different. This is the energy. There was a probability to measure X or Y energy, but I measured this energy, so full stop. This is it. And then the reality for the observer, for the person that made the measurement, is just what they measured. So this maybe sounds a lot more boring, but this is one of the more accepted interpretations. But there are also many other interpretations. For example, cubism, which is quantum Bayesianism, which basically describes that all of quantum mechanics is just Bayesian statistics, for example. But yeah, there are many other interpretations that are also interesting to discuss. But so what is my favorite interpretation? So I personally don't have a particular interpretation that I completely adhere to 100%, I would say, because a lot of the time the differences between interpretations are very subtle. So I don't know if I am like well read enough, in philosophy and so on to really argue for a particular one. But in general, I would say the Copenhagen interpretation makes a lot of intuitive sense, as in quantum mechanics can still be an indeterministic theory where you have to deal with probabilities, probability distributions, and so on. But your reality as a human, as an observer, It's just what you measure. And I think that makes, for me, a lot of intuitive sense. Um, and I feel that arguing for very obscure, abstract theories can get into really big overcomplications, maybe. But at the same time, this is a very in depth topic that is, um, some people, they just have their favorite interpretation. That is the one they argue for. And I personally find myself a little bit more open into accepting certain ideas of some of them, but I personally find the many worlds interpretation very sci-fi. um, but yeah, actually, this is pretty much what I wanted to talk about today. But like I mentioned, if you guys have any questions at all, even to the beginning or anywhere, please let me know. If there was any point where you maybe felt a little bit lost, or maybe just tell me what your opinion is on interpreting quantum mechanics. If you maybe are in a very different field and you think, this really just seems like, just mathematical representations of things, like I don't really get it. um I'll leave the philosophical interpretations to the philosophers. So true, so true. I actually was attending a lecture this semester on a little bit more of a philosophical topic, tying in quantum mechanics to um, basically philosophy and agency in particular. And it was a very interesting discussion, and it honestly, in a way, left me with more questions than an actual answer. Which I guess in a way is good. It didn't just give me, okay, this is the interpretation we follow, full stop, but it gave me arguments as to why some interpretations are maybe better than others. I only know many worlds from conspiracy theories. I mean, if you learn about it through other means, that is also good, but I hope I maybe presented a little bit more of an abstract way of seeing it rather than just seeing it the sci-fi way. Seeing it a little bit more of an abstract uh, way. I also did not really want to present the Schrödinger cat, for example, because of that. Because I find it not very adhered to reality the way that it is sometimes presented, which is, to my opinion, not really the way in which Schrödinger intended it. So that is also why I really didn't want to present that example today. So I'm sorry if you guys were hoping for that. um, uh, yeah, at least I see what you mean by quantum mechanics mainly being probabilities. Yeah, so it's a lot of probabilities, and something that I did not discuss today, which to me is the most lovely thing about quantum mechanics, is when we're talking about entanglement and when really weird things actually start to happen. But Haruhi did not include any of those equations in the first opening. Maybe they are in the second opening. I honestly haven't had a look at that one. Um, but that is what I personally find the most insane. So right now I just wanted to give an overview of how these equations sort of work. Um, Ethics and behaviorism is what they taught me, so it's definitely not related. Well, I feel like there are always ways in which you can tie in certain ethics topics, especially with quantum mechanics interpretation, and basically what is the role of my agent. What is basically what is the person that is doing the measurement, what is this observer that is performing the measurement. So I think there are definitely some tie-ins where you can look at behavior and ethics in that context, but a little bit more in the philosophical sense, probably. Schrödinger cat was parody of quantum physics. Yeah, like I just personally don't really like using that example at all. I personally just don't find it useful. I don't like using that example, especially for an introductory talk about it, I feel like it's not a very helpful thing to discuss personally. I feel like talking a little bit more in abstract terms is maybe a little bit more helpful, as counterintuitive as that sounds. I feel like giving analogies is more confusing. Many words theory was 8-year-old me rationalizing why my pencils always kept going missing. Very true. It was the gnomes. It was the gnomes. The many haruhi theory. Yes, we should write. We should write that one next. Yeah, on the quantum scale, I guess it'd be pretty hard to get a real accurate measurement. So seeing how much it uses probability is funny to be honest. I will actually say something that maybe is a bit surprising. Measurements in quantum mechanics are insanely accurate. Or maybe do I want to give a specific... Okay, I will give one example. So for example, the way the second is defined is via looking at transitions, sorry about the language, atomic transitions in certain types of atoms, or sometimes ions. So time is kept, the definition of the time is kept by looking at these ultra precise, what they call atomic clocks. If you guys are interested, look up atomic clocks. But looking at these ultra precise measurements on atomic clocks. So actually quantum mechanics is extremely accurate. Accurate in the sense of the measurements are to a lot of decimal points, like crazy accurate, which is something that I actually did not like, particularly about astrophysics, where a lot of the measurements are like, plus minus a couple orders of magnitude. We discussed this a little bit last week, and that was personally one of the things I did not really enjoy about astrophysics, because there is even debates as to what the Hubble constant right now is. And I personally find quantum mechanics to be a lot more precise, and it's such an interesting theory that has yielded crazy results and continues to advance a lot of fields in physics today. So a lot of research currently is focused, for example, in quantum computing. Also, like I mentioned, atomic clocks are another really interesting example. And it's a cool field. There's so much to discuss. I only dabbled on the very, very surface today, and I'm sorry if there's anything that still remains a little bit unclear. But I hope this at least gave a little bit of an idea of the meaning of, in particular, the equations shown in the opening, and just a little idea of quantum mechanics. Thank you for following, Bashter. And just a little bit of an idea of what people talk about when they mean quantum mechanics. So it's a complex field, it's a complex theory, but it has yielded so many interesting results. Thank you, maybe not Rob, for subscribing. But yeah, please, I still have a little bit of time for questions. I still have a little bit of energy for questions. So, if there are any last few questions, please just write them down. Anything, even if you guys just want to go back in the presentation and ask something. Like I also mentioned at the beginning, the slides for the presentation are over on my Ko-fi page, which is linked in my profile. And you can download those for free, and you can tell me, for example, in this slide you discuss such and such, like I really didn't get this particular part or this particular plot or something like that. So feel free to, DM me afterwards as well if you guys have any questions. Following that, I want to talk about continuing this series. I will be honest, it was a little bit difficult yeah, how many parts of am I gonna do? So it was personally a little bit difficult to condense such a wide field into just this for this week. It was honestly a lot of work. Um, so I may continue the series every other week. So I plan on doing likely 2 more parts. I believe the next part will cover only particle physics. And in particular for particle physics, I have a lot to talk about, a lot to discuss in there. And we also have quite a few things that are shown in the opening. So I feel like condensing that into a week is unlikely to be a good result. I really pushed myself this week to hopefully bring something comprehensive, but I feel like maybe I missed the mark a little bit in making it understandable to the fullest extent. So I definitely think doing it bi-weekly will allow me to really give it the time and energy that it needs to, really do it justice. So I plan on doing still my weekly streams, but I think next week is likely going to be playing a game or something along those lines. And the week after, I will bring the particle physics presentation. And I believe the last presentation that we're going to have is going to be a little bit of a miscellaneous equations or diagrams that don't really relate to any particular subjects in physics at all that we're discussing right now. For example, the Shannon entropy. And we also have, I believe, benzene, just a drawing of a benzene molecule. So I believe those will be kept for kind of its own miscellaneous category where I will probably, for that one, I will probably have to do a little bit more in-depth research as well. And also there's an equation that I still have yet to identify. So that one I will likely just present and maybe ask you guys, what the heck is this? I don't know. So I've asked a few people and I still have yet to be able to identify that one. So yeah, let's not talk about that one. I'm gonna mention it because I want to definitely write down every single equation that was covered in the opening, but I don't know how much there is to say about that one. Maybe we'll just talk about the notation in general. Just about the math. Okay, what other anime can you teach us from? So I was actually watching the last season of Dr. Stone, and in the opening they have like 200 like equations in the background. So I was actually considering maybe Dr. Stone. And I also was planning on at some point doing the second Haruhi opening as well. Alongside the series, I will hope to also have an article available where a lot of sources are cited. It's a little bit more of a readable text, hopefully, where you guys can just get everything in just, maybe like 20, 30 pages or so, just in one article, just so that it's there, it's documented, we have our information, and it's nice and hopefully concise. Yes, our brains need to cool down. That is true. Also mine. The anime Vsauce. Yes. Hey. Anime sauce. Hime here. I'm citing this stream in my non-curricular lectures. No, I don't know how good this is, but I'm trying. I'm trying to make it nice. Freerun, so we can learn about casting spells. I don't know. I mean, I will be honest. I feel like my forte in all of this is mainly physics and mainly certain areas of physics. So I definitely can look into other things, but looking into other things will take a lot more time. And I want to keep these, semi regular thing that we can discuss. So, sometimes things can take a lot longer to read up on humorism and medieval food medicine. Interesting. I mean, I will say I don't have a very diverse background. I prefer focusing on the physics parts of things, which I personally would like to keep the series mostly to physics, but I'm definitely open to, just seeing random things, for movies as well. It doesn't really have to be just anime, but yeah, we can talk about other media as well. Um Magic is mathematical, read up on bio. Um yeah, and I was saying that with the hot cold particles. Yeah, I feel like that is very interesting. I'm definitely open to having a discussion about maybe how things used to be thought at like in the past and how people discuss things now. What were the accepted theories in the past? Because I read up when I was reading up on all this thermal exchange theory. I read up on, I forgot what it was called, but it was like phlegmaticin or something. I don't even know. It was a really weird word, which basically described how heat flowed. No, how electromagnetic waves flowed as a fluid. I don't remember, but basically they talked about exchange of things through fluids. It was a very strange thing that I read, and that was like what was believed until like before the 1800s. And I think that's cool, and it would be interesting to discuss. I personally have not read that much about it other than just a little excerpt I read when I was doing a little bit of research into the thermal exchange theory, but yeah, definitely would be pretty interesting to discuss. There's nothing wrong with being specialized. Not only did I choose fake science math, I chose a fake branch of math as well as statistics. You can definitely help me out with Shannon entropy then and so on. That is gonna be pretty. That is gonna be a decent bit of reading up just to get some sources and so on it. I love that it lasted for a century, but was a great way to connect what to eat to health. Hot food, cold food, wet food, and dry food. It's insane. Yeah, I think that is, it's interesting to see how people thought about certain things in the past that maybe to us, since we've grown in a complete different time, they just seem so unintuitive and so they don't really make sense at all. But from a sense of I am coming from this background of knowledge, back then, it made sense. It made sense in a lot of ways. So, beavers are fish. Also, capybaras, apparently. um, don't forget the restrictions: soft food for nobles, hard food for peasants. Is there any anime about cyclists? I think you'd have a lot to talk in that field. Um, Not that I have watched, but I know that there's like Haru Ride, I think it's called, and there's a few others as well. But I personally have not watched. I personally have not watched any of them, I will say. But yeah, there's definitely a lot of animes that cover, weird things. I also considered Steins Gate, but I honestly, I will say I am not the biggest fan of Steins Gate. I will admit. I will admit I am so sorry. Um I don't hate it, but it's just not my favorite. Uh Yowamushi Pedal. Yeah, I also heard about that one. I've also heard about that one. But yeah, I personally have not watched any cycling anime. But yeah, please let me know if you guys have any questions. I'm sorry if I didn't do the greatest job of building up from 0 to 100. But I hope it at least gave you an idea, at least gave you a little bit of intuition as to where quantum theory came from, what it means to quantize, because I feel like it's a word that gets used in very different contexts. And then moved on to, just a little bit of an overview of quantum theory. And like I said, we haven't even brushed the surface of how much there is to read, do, etc. in quantum mechanics. I hope it at least gave you guys a little bit of an introduction into what people mean when they say quantum mechanics. So yeah, so this was my presentation, and like I mentioned, I have the slides up. You can ask me any questions that you guys have right now, or DM me afterwards. I hope it was a nice little introduction. At least it piqued your interest a little bit. A lot of the math is it really builds up on itself, and it would be a really long course. But if anyone is interested in discussing linear algebra in the context of quantum mechanics, starting from like into that, but that would also take, a lot of time and resources and so on. But I actually enjoyed linear algebra, I will say. In Steins Gate, they change a character's sex by telling his mother to eat more salad. I know. That's what I'm saying. I don't know. I don't hate Steins Gate, but I also don't love it. I feel like it's a little bit overrated. I'm so sorry. I'm so sorry. Thank you for the explanation. It was interesting. I'm glad. And yeah, I hope it piqued your interest a little bit. If you guys need a recommendation on books, I really recommend the Griffiths quantum mechanics book. Very theoretical, but it starts from the ground up. It's a really long book, but very, very theoretical and nice. And if you guys are not so interested in looking at a super theoretical book, more so in the field of quantum computation, there's one nicknamed Mike and Ike. Also, I had it for one of my lectures. Also, great book. Look up Mike and Ike quantum mechanics, or I believe quantum computing, something like that. You'll find it. That is more so on the application side of things. So the explanations are a little bit more summarized and concise. Sorry. Anything to distract me from my real course is so true. I'm almost done with my semester. I will hopefully be graduating in just a few months, so that is really exciting. But also really nerve-wracking. I think these streams are maybe helping me a little bit in the sense of if I maybe would be interested in going into something in the realm of, talking about science, like science communication and so on. But yeah, and by hopefully, I mean, I think I should graduate in July, but it may extend to August, something like that. But I definitely should be graduating at some point this summer, so in a few months. But yeah, so I hope you guys found this interesting. I hope I communicated everything that I wanted to communicate. And yeah, like I mentioned, next week I will be streaming something funny, a game or something a little bit more chill. But we will be discussing particle physics in 2 weeks, where I hope I will bring you guys a very nice explanations, and also a lot more experimental stuff, which is, I think, what you would also be, and you guys find the most intuitive and the most easy to follow. So I will hopefully bring a lot of that to the table next time. And yeah, and so I really appreciate anyone that came, especially if you guys stayed up until this point. I know this was a little bit of a long presentation. I was, last week it was about an hour. This week almost double. So I hope that it was helpful. I hope that it made you guys interested. I hope that it at least gave you a little bit of an intuition as to quantum mechanics is, and yeah, understood it at least a little teeny, at least more than before. At least more than before you heard it. So yeah, thank you so much for putting the time. Yeah, I am finding these the research for these streams really enjoyable. This week was just kind of a week where I had to do a lot of things, so I was only able to dedicate most of the nights. So I dedicated maybe like 3 or 4 nights to working on the presentation. But hopefully by doing it bi-weekly, I will have a little bit more time to prepare, and also hopefully have a little bit more time to just make it accessible for everyone, which is kind of my goal, to try to make it accessible for anyone that is open to learning about weird subjects. So many Wikipedia tabs open right now. See, like that is my goal, to make you guys be like, oh, this thing sounded interesting. Maybe I want to know a little bit more about it. So just side note, on the realm of talking, or on the topic of black body, I also, you can actually very closely, Frolic has to go. Bye, Frolic. Good luck in your class. In the topic of black bodies, you can actually really closely approximate the sun with a black body. And that, the first time I heard that, it's like, what the frick? Like, what does that mean? How can you approximate, like, a black body absorbs all radiation? Like, the sun is definitely giving out a lot of radiation. Like, what the heck? So the thing with the sun is that really most of the radiation is contained inside the core. None of the core, or really little of the core, is actually coming out. And the little bit that does get scattered out is what makes it differ from a black body. But you can actually really closely approximate the sun with a black body radiator, which I find really interesting. But yeah, so just a side note, just an example that I didn't really want to bring up because I thought maybe it would be a little bit confusing. But yeah, something like 9 years. I don't know what the probabilities are for photons to get out, honestly. I know, like, the thing is, the outside, like the surface, is the one that is kind of found in thermal equilibrium. So it basically is like a sphere. It's basically like our sphere with the hole. So it's like a sphere holding in this core of radiation that is just bouncing inside, with like a thermal surface at equilibrium, with a surface on top of a thermal equilibrium. So that it's just kind of crazy. I don't know what the probability of photons getting out is. I don't know if it would be like 9 years. I don't know. I genuinely, I don't want to, I don't know, but it's just crazy to think about the fact that you can describe it with something that seems so different. And especially, this is a question that I thought I was gonna get asked at some point. Doesn't a black hole literally sound like a black body emitter, maybe it's something you guys thought about. Maybe you guys thought, oh, that's a stupid question to ask. So I don't know if you guys thought about that question, but interestingly, like black holes have a particular kind of radiation that has actually been it has been measured, I'm pretty sure, and it's called the Hawking radiation. So it's a really small amount of radiation that comes out of black holes, and it's related to, I believe, the mass inside of the black hole. Look, fact check me, but I'm pretty sure the mass inside of the black hole. Anime girl smile has more radiation than the sun. Very true. Also very true. Anime girls. Hawk too, yes. A bit unrelated. The sun's magnetic field also protects us from cosmic radiation, right? Is that due to the core as well? I don't know what the exact field lines are inside the sun. This is a little bit outside what I can, my expertise, so to say. Maybe I'll have a quick look as to what that looks like. Let's see. Let me see what exactly causes this heliosphere. Okay, so it basically comes from, just a little bit of a summarize from charged particles that are generated by the sun itself. So by the basically by the solar winds coming from the sun. The solar winds are these charged particles that are spewed in this fusion process going inside the sun, and that is what protects us from cosmic radiations. So I hope that makes a little bit of sense. Yeah. But yeah, like I mentioned, I will say my weakest physics knowledge is probably in astrophysics, because I used to find it very interesting when I was younger, and then I was like, I don't like this actually. I don't like this actually. So I'm sorry if I don't have the best answers. Mad fact, my old physics teacher was working with Hawking's when he was working on that. That's cool. That's really cool. I have only met one famous physicist, and it was kind of by pure weird chance, and it was Nobel laureate from 2022, I believe, 2023. Anton Zeilinger. But yeah, actually really, really nice guy. If you guys have heard about him. That's the guy that maybe you guys have heard of, like, you know, teleporting particles through quantum mechanics. Just weird stuff that you can do. Some nuances in there. But yeah, that's the guy that did those cool experiments on that. What else? Atomic physics are the coolest, signed non-physicist. Maybe. I guess I don't completely disagree. I don't completely disagree. I think it is. But also, atomic physics is Schrödinger. I'm so sorry. I am so sorry. But if you want to know about atomic physics, you need the Schrödinger equation. Like, 100% of the time. Very cool though. I really like atomic physics. Another thing that I thought was interesting that we can maybe discuss at some point, just in my last 5 minutes that I'm here, proton radius, atomic physics. Proton radius is basically quantity that's kind of debated, interestingly enough. Think something that you would think that people have measured to extremely high accuracy. Something that is a little bit challenging to accurately measure. So yeah, cool thing. If you look up proton radius puzzle, I had to give a little presentation on this last year. But yeah, atomic physics, very cool, also very quantum. But I hope this gave you guys a nice idea into this. I have repeated that probably 5 times, but also you can ask me questions. Also repeat that like 5 times. But yeah, I think I will be leaving for today, and I will continue with the series until we have achieved at least attempting to explain every Haruhi equation. I hope I will be improving with time in the explanations, but I hope we at least achieve a little bit of an understanding in the equations shown in the Haruhi opening, and maybe an idea of why they could have chosen them. But yeah, I hope you guys had a fun time. I will be leaving, but yeah, thank you so much to everyone for coming, and I hope the explanations and everything keeps improving. I will try to point you guys in the right direction if you guys have any related questions to what we discussed. But yeah, thank you guys, and